Hello and welcome back to our introduction to AC motors, where you'll notice that this slide is one of the same ones that we used in the last video to explain the fundamental nature of how you get rotation from AC input. But I wanted to use it to point something else out, and that is that if we have a very simple AC motor like this one, then we have a very large difference in the amount of torque that the rotor is receiving at different points on the curve of input voltage. So at this point, let me grab that, okay. So if we were looking at this instant, there is actually no voltage being supplied to the electromagnets here, which means that the current flowing through the electromagnets would essentially be zero, which means that the field created by the electromagnets that's going to push and pull this rotor, this permanent magnet on the rotor, around and around and around, well, those poles are either non-existent or very, very weak, residual magnetism kind of stuff. And so the amount of force, and thus the amount of torque on the rotor, will be very low. And then we'll get stronger and stronger and a little bit weaker. And then again, for a moment, now of course the velocity of the rotor is non-zero, right? It's rotating away. But at this moment, there's no voltage being applied by the AC source. There's no current running through the coils. And so there's no magnetic field that's exerting a force on the rotor at this point. And you can imagine that if you had a motor like this, you'd kind of get this herky-jerky torque on the rotor, which if you're actually using it instead of just sort of as a demo to show how these things work, if you're trying to use it in a practical circumstance, then you have a torque that is not very smooth, a torque that is 0 here and 0 here and 0 here, and then varies as you move up and down in voltage and thus up and down in current through the electromagnets. And I mentioned this just for a moment in the end of the last video, is that part of the reason, in addition to having a predictable direction and all that kind of stuff, but a big reason why you would want, in this case, a dual phase, so two different sine waves from two different power sources that are offset in time, so this one achieving a peak here and this one achieving a peak sometime earlier, and that sort of fixed offset remaining the same as this oscillates back and forth. Well, one reason is that you get this predictable direction of rotation, and you have the rotor following the magnetic field around and around and around, a rotating magnetic field from the stator causing a mechanical rotation of the rotor. The other thing that this does for us is that it smooths out the torque that is going to be felt by the rotor, because you'll notice that at no point anywhere along this time axis is there no current going to any of the electromagnets. And so the rotor is always going to be feeling a force, trying to follow that magnetic field, and so is always going to be receiving a torque. And this gets more complicated, as you might expect. So for example, we've got here a three-phase version of a three-phase version of this synchronous AC motor. So synchronous meaning that the rotor is, once it's rolling along, is going to exactly track the rotating magnetic field around the stator. So that tracks with the direction of the rotation here. Oh, but it's different in this diagram than the last one. So I guess the rotation of the magnetic field must go this way here. Let's erase it. There we go. Get things properly done here. All right, so in this one, the magnetic field direction, so the net magnetic field created by the magnetic field created by each one of these pairs of electromagnets, each pair of electromagnets being driven by one of these sine waves of voltage. causes a rotating magnetic field in this direction, which in turn causes the rotor to follow that magnetic field and rotate in that direction, as you can see in the subsequent cartoons here. And the basic idea is that each one of these, if we're looking over here on the right, or sorry, the left, okay, I know left from right, sure, is that each pair of the electromagnets, and I've color-coded it to match the color coding over here, okay, each one of these is being fed by some AC source. All right, so this would be, say, phase 1, and then this one would have connections to another one that would be phase 2, and then this one, last one, would have connections that would go to phase 3. And of course, you'd have to complete the circuits around from electromagnet to electromagnet, like this, for example, for the red circuit. So you had a complete circuit. But that's the idea. So you get that 3 separate power sources, just like we had 2 separate power sources here. Now, in practice, this dual phase kind of setup, where you have 2 different phases, usually isn't because you have just 2 separate generators that you've very carefully tuned so that they're offset this way. What you normally have is a single source, and then the second pair of electromagnets, say the horizontal pair here, would be a parallel branch from the red ones, and in that parallel branch you'd put a little capacitor. Okay? And the effect of the capacitor in series with the windings in that branch would shift the voltage signal, and thus the current flowing in that branch, relative to the other branch. And so you'd get effectively this same offset in the peaks of the voltage in each pair of electromagnets. That's how it's done for things like motors that you would find in a washer or dryer, or a dishwasher. All kinds of household AC motors use this technique to get dual phase. They put a capacitor in parallel, or in a branch that is parallel, so that you get this split, this phase shift relative to the 2 pairs of electromagnets. Now this, the 3-phase version, well, typically, and let me get rid of the ink here. Typically you don't play tricks with capacitors. You'll notice that these all have a very nice, even phase split relative to one another. If you look at the offset in degrees, so 360 degrees to go through one cycle of the sine wave, then these 2 peaks are 120 degrees apart. Okay? And the other one is 120 degrees apart as well, and so each one of them is sort of a third of a cycle off from the other, one ahead, one behind. This 3-phase operation is typically done in industrial settings, and that's because that at a sort of power plant, power grid kind of level, power transmission is done in 3 phases. So you've got a neutral wire and then 3 wires, each one of them carrying one of these 3 phases. Okay? So if you look at transmission towers and things like that, that tends to be how it's split. And in households, we just get a single phase, and we have to split it using that capacitor trick. In industrial facilities, they tend to get the full 3 phases, and so they can just hook up the appropriate wire to the electromagnets here on the stator, and all is well. Worth mentioning that the way they get 3-phase power at the power generation side of it, so if you're thinking about the generator that creates this, well, you can have a 3-phase generator. I mean, just look at this thing. If we, instead of putting in AC to these electromagnets, if instead we, and then, so put in AC, get rotation. If we didn't put in anything to these coils of wire, and instead we took our hand, or more likely something much more powerful than that, and we rotated this permanent magnet here. Well, we would be changing the magnetic flux through these coils, right, as we swept this magnetic field source by. So if you go back to Faraday's law and generators, you know that you're going to be inducing a voltage on this pair of electromagnets. And as this thing rotates, you're also going to be inducing a voltage on the green pair and the red pair. And the only difference between the electricity that comes from each one of those independent pairs of coils is the fact that, well, when the blue one is at a peak, okay, the green and red ones are going to be smaller, okay, and negative, and offset by 120 degrees. And this has everything to do with the geometry of these coils as far as they're offset by a third of a turn as you go around the stator. Okay? So a little bit about multi-phase AC motors. When we come back next time, we'll talk about induction motors, which are far more common, as it turns out, than these synchronous AC motors that we've been talking about. See you then.